Well, this is a part of a project that Sergei Pisaresky and Steve Pitts and I are working on. And the question is plate tectonics speeding up or not speeding up or staying the same? As the mantle cools, stress increases at the base of the lithosphere. Coupling between the lithosphere and the asthenosphere increases, and plates should move faster. But we've got one problem here, well, maybe more than one. Water has been recycled back into the asthenosphere over time. In fact, there may be 1 or 2 oceans of water down there, some people think. Thus, the coupling between the lithosphere and the asthenosphere remains constant or perhaps decreases, and plate speed should not change with time or actually be slower. If we look at the temperature of the mantle with time, one way of getting at this is by calculating the mantle potential temperature, which is plotted here, based on chemical calculations of major elements. In particular, the iron and magnesium are important, using methods such as Claude Hertzberg's method or Sintelese. And here we have data as a function of time calculated from basalts, largely oceanic affinity basalts, and shown on here with the red squares are the median values with 1 standard deviation. And as you can see, with time, the mantle potential temperature has fallen off. Today, it's around 1380 or so degrees C. But as we go back in time, the temperature gets higher and higher in the mantle. And thus that degree of coupling between the lithosphere and the asthenosphere should get weaker as we go back in time. Just summarizing this, we know that really there's been a great thermal divide or regime divergence here. And this is in our 2016 paper that we proposed this. If we look at basalts back through time, some of them appear to not show this decrease to 1350. These are the ones that appear to be plume related and have enriched mantle sources. And somewhere around the end of the Archean, we proposed there was a thermal divergence, and we got these 2 different types of mantle. And the one we're going to be focusing on, of course, is the large volume of mantle, the ambient mantle, which does show this. We suggested that there was a transition here, and before this time, the Earth was in some sort of stagnant lid regime, and afterwards, it evolved into a plate tectonic regime. Now, Jim Korinaga, back in 2006, published a very interesting paper, and he suggested that the plate speed is increasing with time. If we look at the lower left diagram here, which shows average plate speed with time, in his model, he's got the plate speed increasing with time. Well, that really was perplexing to a lot of us because that's sort of counterintuitive. If the mantle was hotter in the past, it should be slow. It should be faster then, not slower. And yet he showed it in his model speeding up with time. But he still shows the same thermal regime. You can see here that the mantle is cooling with time, okay? He has a little bit higher temperature here in this model, but it's still cooling with time, and the speed is picking up. So what's going on here? We have looked at this from a variety of ways, and if we start here and look at the supercontinent cycle, what I have plotted here is what I call the stagnant lid stage of the supercontinent cycle. And that's equal to the maximum packing of plates minus the breakup, the start of breakup. If we look at the 3 supercontinents that we're familiar with here, the purple dots down here, the first purple dot on the left represents the beginning of assembly. The second purple dot is the assembly of the major assembly, and the third purple dot, or the maximum packing, and the third purple dot is the first breakup. And the fourth purple dot is maximum dispersion. And I've shown that for each of the 3 major supercontinents. Now, of course, this varies depending on whose reconstruction you use. The reconstructions I have used are shown referenced down here at the bottom. but I've also looked at other reconstructions. In this reconstruction, the lifetime, or the stagnant lid phase rather, varies from 100 million years in Nuna, 50 to 20 million. It decreases through time. The same thing is observed with other people's reconstructions. The actual magnitude or the length of times vary depending on the reconstruction, but the trend is the important thing here, decreasing with time. It's like the coronavirus. It's important to see that the trend is decreasing with time. The magnitude is not so important. Well, let's look at some ways that we can actually test this. Steve Pitts and I have been working together for several years now, looking at large zircon databases, and this is a summary of the time series for igneous rock database and detrital zircon database. At the time I made these diagrams, or Steve made them, we had about 200,000 zircons in the igneous and about 600,000 in the detrital database. Superimposed on here, I have shown the supercontinent reconstructions based on the reference before. Yellow would be the assembly phases, tan the breakup phases. Down here I have epsilon hafnium with time. I'm not going to have time to talk about that today, but if we look at the zircon distribution, something we have known for a long time, but now we can quantify very vigorously, is that the frequency of the zircon peaks increases tremendously, especially in the last 800 million years ago. You can see the frequency of the peaks increasing here. Not only does the frequency increase, there's a change in the spacing of the peaks, which I'll come to in a few minutes. Now, that increase in frequency is at least consistent with the speed up in plate tectonics. It's not the only explanation, of course, that could be offered there. So how are zircons related to plate speed? Well, where do we get the zircons from? Most of them, even the detrital zircons, come from granitoids. So if we look at the history of granitoids, we can track the history of zircons. And here are the two types of major origins we have today, the accretion and the collisional type origin. If we look at the accretionary type origin, as we're dehydrating the plate and we partially melt mafic material here in the lower crust under hydrated conditions, we get granitoids. In collisional type, you see the same thing. As we depress metasediments, metavolcanic rocks, other older rocks, we partially melt. These guys, we can get granites. And if we get granites, we got zircons in the granite, and eventually these guys are elevated to the surface and eroded, giving us detrital zircons. So if we look over here, how is plate speed tied in with zircons? As plate speed increases, we're going to increase the granitoid production. If we increase the granitoid production, we're going to get more zircons, both the igneous and eventually the detrital zircons. This is a map that Sergei Pizarevsky put together a few years ago, and we published it a couple of times. That it just shows a distribution at about 1650 MA of accretionary and collisional origins. And the collisional origins shown in red are responsible for the development of the early cratons here that developed in the first supercontinent. They're the glue, of course, that holds these pieces together. The accretionary origins are shown largely around the perimeter of these, with one accretionary origin being particularly prominent. This is number 35 here. This is the Great Proterozoic accretionary origin along the west coast of Laurentia and Baltica. Going into India in this reconstruction, some put Amazonia down here, and in that case it would go into Amazonia. Now, let's look at the relationship between origin frequency and zircon age peaks. And what I have plotted here is origin frequency. In our spreadsheet for origins now, we have 250 or so origins in the last 2 billion years in the spreadsheet. And that's what the red histogram represents here, is the distribution of these origins with time. And of course, we get peaks with time. And then I have shown on this diagram with arrows the major zircon age peaks from the previous diagram, okay? So if we go during Nuna assembly here, we have a large peak here at about 1900 or so in origins. Well, we have a similar peak in zircons, 1900, okay? If we go to the other ones here, there's a peak at 1200, there's a zircon peak at 1200. Peak at 1000, zircon peak, 600, 450, 250 to 300, and 100. So there's a one-to-one correspondence between the major origins, the frequency of the major origins, and the zircon age peaks, which gives some support for that previous slide that I just showed, the relationship between the zircons, granites, and plate speeds. Now, if we look at the spacing between these peaks, the origin peaks or the zircon peaks are the same. This is actually for the zircon peaks. We have the spacing of these peaks in millions of years on the vertical axis versus time. There's an interesting relationship here with time. The spacing of these peaks gets closer and closer as you come to younger and younger. We start out over here back at 1200 or so, with the spacing being, what, 800 million years or thereabouts. It drops with time, and it especially drops in the last 600 million years. We're less than 200 million years spacing between the zircon peaks. Now that's something that is at least consistent with plate speed picking up. It's not the only explanation that can be offered for that, but it's consistent with that. Now, let's look at the frequency of collisional origins. And this is a diagram which we first published back in 2015, and I have updated it based on our updated spreadsheet for origins. And there are two major features that show up here. Superimposed on here again is the Supercontinent Cycle, blues for assembly, pinks for breakup. On the vertical axis, we have the number of collisional origins in a 100 million year moving window, okay? That's what each one of these dots represents. With time, two things show up on this diagram. There are peaks in the frequency of the collisional origins, and if we fit these to a moving average, the number of collisional origins is increasing with time. Interestingly enough, we see a big peak here, which is at the beginning of the assembly of Nuna. We see a peak here at the beginning of the assembly of Rodinia. We see a peak here at the beginning of the assembly of Gondwana Pangaea. That's not perhaps unexpected. As these supercontinents begin to form, we'd expect a lot of collisional origins between the cratons. But what is interesting is if we, even though there's a lot of noise in here, is if we fit the data to a 100 million year moving window, the average is over 100 million years, that indeed the number of collisional origins with time appears to be going up. Back here in the 2 billion years ago, we're down around 2 per 100 million years. We're up in excess of 6 per 100 million years in the last 100 million years or so. You'll see these T1, T2 on these graphs. I don't have time to talk about these. These are two major transitions of Earth history in a paper we have in the press now. If we look at the distribution of cratons before the assembly of Nuna, I've shown them here, there are 36. Now, the distribution doesn't mean anything here. This is just arbitrary. And in fact, most of these cratons were separate from each other. If you look at Laurentia here, they're all fitted together as they will be later, but they were not at the time that before the assembly of Nuna. But the important thing I'm trying to show here is there was at least 36. There were probably others that were smaller than this before the assembly of Nuna. If we come up to a more recent time, this is, I can't see the top of my screen there, but anyway, there are 14 cratons. This is sometime in the mid-Proterozoic. I don't recall exactly, and there's a bar covering up the text on the top of my screen. I can't see it. But by this time, we have 14 cratons. So we dropped from 36 to 14, okay? And now all those cratons in Laurentia are amalgamated together. Again, the distribution of them here is not a reconstruction. It's just an arbitrary distribution to show you the names of the 14 cratons we've had. So we had a real decrease in making Nuna in the number of cratons. And this shows up on this diagram, which shows the number of cratons over here. It's divided by 2 versus time, again with the supercontinent cycle superimposed on here. But if you look over here now, prior to 2 billion years ago, we had in excess over here of 30 cratons. You multiply this number by 2 over here. But between 2 billion years ago and 1.8 or so is when we had the first amalgam, starting in the amalgamation of Nuna. This dropped very, very rapidly. Very, very rapidly. And now we're down at the order of 12 to 15 cratons from then on. There does seem to be a slight decrease with time, but that's within the uncertainty. Most of these cratons amalgamated during the amalgamation of Nuna, and after that, we really didn't break them into small pieces again. They stayed as fairly large pieces of time from that time on. If we look at the ratio of collisional to accretionary, okay, over this period of time, we see another very interesting relationship. Associated with Nuna, the red dots back here, this ratio is greater than 1. There are more collisional origins. But by the time we get to Rodinia and Pangaea, this ratio drops to less than 1 for most of them. There's a decrease here, especially at the end of the Nunian era back here at 1200 or so. There's a decrease in this collisional accretionary origin. This is something that's not fully understood yet, but clearly the ratio is much smaller after this time. Paleomagnetic plate speeds. This is something that Sergei put together for our 2015 paper down here. This is where plate speed in degrees per 100 million years is plotted upon a function of time. Again, we see 2 different features. We see peaks, and we see an increase, as shown by the moving average here in plate speed with time. Now, the peaks do not correspond as nicely to the supercontinent cycle as we'd like to here. For instance, the first peak here is during a breakup of the late Archean supercratons, if you want to think of that. But after that, here at this point and this point, the peaks are in the assembly times of supercontinents. Anyway, the important thing here is this speed is picking up. Down here, it's of the order, say, at this vicinity here, we're the order of 20 degrees per 100 million years. We're in excess of 40 by the time we get up here. Another interesting thing to look at is passive margins. This is Dwight Bradley's original publication, where he showed that passive margins occur in spikes here that are related to supercontinent or supercraton breakup, supercraton in the one here at 2 billion years ago. But he pointed out that associated with the breakup in Nuna, there's not much in the way of passive margins. There's indeed low there. Well, we have been working on that, or I have, looking at it in terms of the probable passive margins based on the paleomagnetic reconstructions. And over here I have a diagram that shows a number of passive margin start dates. And again, the supercontinent cycle is superimposed on here with blues as breakups and yellows as assembly. But first of all, we have this big peak here that Bradley showed also at around 2 billion years, which is the breakup of the late Archean supercontinents. But the important thing is here, if we look at the breakup of Nuna, we see evidence in the paleomagnetic data that we have to have many more passive margins. And I've come to a number around, I think 12 is the minimum number we have to have here. So indeed, there is a peak showing up here in the breakup time of Nuna. And then of course we have a peak over here in the breakup of Rodinia and Pangaea. If we look at the passive margins lifetimes through time, here it is in millions of years. And this is something that Dwight Bradley originally pointed out from his work. We definitely see a decrease in their lifetimes through time. Up here at 1500 or so million years ago, we have a lifetime of, let's see, 600 or 700 million years, dropping off to less than 200 million years. Again, this is something that is at least consistent with increasing plate speeds. Now, we've also looked at lips and what they are telling us. And this is one model for lips where we have how lips might be related to subduction. So slabs accumulate in the deep mantle. They're swept into the large low velocity provinces, and this is where we get plumes developed. And plumes gives us lips. So if we have faster subduction, that should give us faster growth of lips, more plumes, more lips. Well, we can test this because we have a time series analysis made by Steve Pitts of the lips. And in the next slide, I'm showing that. I also show the zircon data that I showed before for igneous and detrital zircons. But the lower graph here shows lips with time. And you can see here, there's really no evidence of an increasing frequency of lips with time. Now, there's this one big peak here at 100 million years. That includes oceanic lips. Before that time, oceanic lips are rarely preserved, so this is just continental lips. If this were just continental lips, this peak, it would be way down here. And if anything, you'll notice while we're increasing frequency of zircons, we may actually be decreasing in frequency of lips, if anything. So that doesn't look very good for the speed up for the previous model, if the previous model is correct. Now, we've also looked at lip center, where a lip center is where we have a high density of lips. Here we have one of Sergei's reconstructions at 600 million years ago. This is Laurentia. This is Baltica. There's a large number of lips around here at 600. By 550, we've opened an ocean basin between Laurentia and Baltica. If we look at it a little older, this is an example at 1350, where we have here Mawson and the Australian plates here, which will become Australia. And down here, this plates, which are part of Siberia. Well, we have a lip center here, and by 100 million years later, we've opened an ocean basin here, okay, between Siberia and Australia. If we look at the frequency of the lip centers with time now, we also don't see an increase in their frequency in particular. There are peaks in here, but there's no really compelling evidence that the frequency of lip centers are increasing in time. We have a big peak back here, interesting, just before Nuna began to form. This peak, again, up here at 100 million years includes oceanic centers, so it's a little misleading in that respect. This is an interesting outcome of this particular aspect of the study. This shows the number of lips per center that either are or are not associated with ocean basin opening. The blue ones are associated with opening of ocean basins, the red ones are not. And they're plotted as a function of time here. And the interesting thing that comes out of this is whether they're associated with opening or non-opening, there's an increase in the number of lips per center with time. and particularly a big jump here in those that are associated with opening in the last 600 million years. We don't know what this means, at least I don't know what this means yet. This has just come out of our studies. It's something that's really brand new. If any of you have any ideas on this, we would certainly welcome your suggestions or ideas. But the number of lips per center definitely appears to be increasing with time. And to me, as I say over here on the right side, this suggests that although we're not increasing the number of lips, we're changing their geographic distribution. They are regrouping, okay? For some reason, they are regrouping time into lip centers. Okay, now if we look at the average time between lip activity and ocean basin opening, this is shown on here in terms of median values with one standard deviation of the mean, shown for the three major supercontinents that we're talking about here. And this is one thing that it's very clear, that average time between lip activity and ocean basin opening. These are for the lips that are associated with ocean basin. But that's dropping off with time. There's no doubt about that. That's dropping off with time. And that is consistent with the supercontinent cycle speeding up. It's not the only explanation, again, probably. So this is a summary of the 6 points that I made here. Stagnant lid stage of supercontinents decreases in the last 1.5 billion years. The frequency of collisional origin increases. The spacing between origin or zircon, either one, age peaks decreases, okay? And the frequency increases, especially in the last 1,000 million years. The paleomagnetic calculated speeds increase since the Archean. Passive margin duration decreases. And the time between lip center activity and ocean basin. Now, all of those are consistent with plate speeds picking up. Any one of them might be, interpreted in some other way. But all 6 of them together, to me, really suggest that plate speed is picking up. Well, that doesn't end our problems, though, because we know that there's a lot of water in the mantle, and this water has been recycled back into the mantle at subduction zones, especially in the last 2 billion years when plate tectonics has been widespread, if not before. And water has the opposite effect that we'd like to see in the asthenosphere in terms of viscosity contrast. Oh, this is just a list of some recent papers in the last few years that show how important water is in the mantle. The amount of water in the mantle can amount to somewhere between 1 and 3 oceans of water, most of that being recycled into the mantle since subduction began. If we look at the effect of this in terms of viscosity contrast, at the base of the lithosphere, an important feature that would be related to the speed of plates is the stress that is transmitted across this boundary from the asthenosphere. And in today's mantle, there's stress transmitted across here, which is in part responsible for driving the plates. Of course, the sinking of the plates into the lithosphere, the subduction zones themselves are probably the greatest force driving the plates into the mantle. But if we look at the effect of viscosity contrast on this, plotted down here are some vertical sections. Today, if we take the blue line here, which is related to the geotherm, okay, in the lithosphere. Here's the mantle 80 of that going up, and here's the geotherm. This is the lithosphere, asthenosphere boundary. We see there's very little contrast in viscosity. They're essentially the same. So there's a lot of stress transmitted along that boundary. But if we go back in Earth history when it was hotter, the effect of heat is to increase that viscosity contrast, which decreases the amount of stress at this boundary. And interesting enough, if we pump water into the mantle, we hydrate the mantle, depending on how much we hydrate it, we can increase that viscosity contrast even more, as shown here with this hydrated curve. So if we are pumping all this water back into the mantle, we shouldn't see plate tectonics speeding up with time. We should see it slowing down because the stresses are less at this boundary if this is very weak. Okay? So we got a problem. June Coronata, he pointed this out in his earlier models. Here's one of these models for a dry mantle model. What we've shown here is plate speed versus time. And you can see in the dry model, the plate speed, his model goes up by a factor of 4 in the last 1.5 billion years or so. And that's due to a significant decrease in the viscosity contrast. But if we got water in the mantle, here's his wet mantle, it only goes up very slightly, or perhaps not at all, depending on the amount of water you put in the mantle. It can stay constant, or it might even drop off. So this wet mantle could have just the opposite effect that we'd like to have. So if the observations, the 6 observations I pointed out earlier reflect a speeding up of plate tectonics, somehow that water that's recycled in the mantle has to skip the asthenosphere and mostly reside in the deep mantle. It can't go into the asthenosphere because it weakens the asthenosphere and has the opposite effect. Interestingly enough, we look at what happens to water in subduction zones. This comes from a model of Facenda in 2014, which he very nicely shows. Unfortunately, the thermal contour lines do not show up very well, but this 1300-degree line, isotherm, which goes down here, this is a subduction zone going down. And it comes back up over here. You can't see it, but it's in here. That's usually taken as the base of the lithosphere, okay? The blue on here represents the water that is coming off of the dehydrating lithosphere. And the important point in his model is that this water is not going up into the asthenosphere, but it adheres closely to the top of the plate and eventually goes up here into the mantle wedge in the lithosphere, which is very interesting because this gives us a way to skip having this asthenosphere continuously hydrated here with time. But where does most of the water go? Well, this comes as a summary slide from a lot of the high pressure work that's been done in the last 10 years on hydrous minerals at high pressures. Over here we got temperature, here we got depth, or gigapascals down here. If we look at the slab geotherm, or a typical slab geotherm, we can see as we start to go into the mantle, the green over here, this is the stability of antigerite or serpentine mineral. We can see that stays stable to, 250 kilometers. That's the base of the lithosphere. So you can take water in serpentine a lot deeper than we thought we could take it. And then if it transfers into some of these other phases, some of these phases don't even have names. They're given letters in the alphabet, but they contain water at high pressures. In particular, Wadsleyite and ringwoodite can have up to 1,000 ppm water. That's amazing, 1,000 ppm water. Wadsleyite's produced at the 4 to 10 kilometer discontinuity here. And this would be the base of the 660 kilometer discontinuity. So basically, what might happen here is somehow we skip the asthenosphere because these minerals are stable, and we take this water into the deep mantle, okay? And so that removes this problem that we have of hydrating the asthenosphere and making it weaker. And this sort of summarizes that. This is my last slide here, incidentally. If we have a subducting plate here, here's the asthenosphere. Somehow we have to get the water that is in the subducting plate, most of it which has been acquired by alteration at the mid-ocean ridges or sometime during its transport. We have to get it through the asthenosphere and into the deep mantle. Well, those high pressure phases, most of them are stable and can carry it into the deep mantle, even antigerite, as I pointed out, okay? So the bottom line for this mantle is the mantle is cooling, the lithosphere asthenosphere viscosity contrast is changing, and the coupling is increasing. The contrast is decreasing, and the average plate speed could be increasing with time. Okay, I think I'll stop there and see if anybody has any comments or questions. I brought up a lot of questions, actually.